Thanks. Yeah. I want to go through factor analysis and continue our tour of EM because it puts us in this position where we are going to have to make some pretty serious modeling assumptions to make progress. And it's going to kind of force us to walk through what that looks like in an unsupervised way. So that's what the factor analysis piece is. We will then cover a little bit of PCA, which is an old standby. And it's good to contrast these two kind of methods together. It's kind of the old, more less Bayesian, less probabilistic standby that people use a lot in unsupervised learning. Just to give you a sense of where we are in the course, up next for us will be this problem called ICA, which will be great. That's going to be in your homework. It's always one of people's favorite homework problems. This is the cocktail party problem, which we'll go through. And if we have time, I'm not sure we will, but if we have time on our current trajectory, we'll go through something called weak supervision, which is a setup that looks just like EM, this expectation maximization setting, except for we can solve the underlying problem exactly. So some folks were asking questions last time, hey, why don't I run method X, Y, or Z on this? And there are these latent problems where actually you can cut to the chase and exactly solve to the right answer. You don't have to run this kind of back and forth style algorithm. And so we'll see that if we have time and kind of give you a sense of why that's interesting. This is more modern stuff that we'll talk about. All right? Now, on to factor analysis. This is what we're going to talk about. And this is a setting where we have more dimensions than we have data points. Now, just by way of history, when we used to give these lectures about factor analysis, it seemed like kind of an odd situation. Why would you have so many more dimensions that you cared about in your model than you have data points? But actually, weirdly, like if anything in the last couple of years, modern machine learning has switched to that being almost the default. We tend to train much, much larger models, as you saw, than we have available data. And there's a couple of reasons for that. They're not the reasons that are in factor analysis, just to be clear, but this setting is actually a pretty interesting one. And so we'll see how people addressed it initially. Right. Awesome. So let's talk about factor analysis. Factor analysis. All right. So we have many fewer points, data points, than dimensions. That's the setting that we're in, okay? And kind of terse notation, this is n is much less than d, okay? So it's worth comparing this, by the way, with GMMs. In GMMs, if you remember, we had only a couple of parameters, right? We had the source centers, we had the source variances, and we had the kind of fraction that were in each source. But we assumed implicitly we had a ton of photons, if you remember, from all of the different things that were going on, from all the different sources. And so n was much, much greater than d, okay? And that was kind of implicit in what we were doing, but it's worth calling out. And the reason is we would average over some sources, and we didn't have to worry about a couple of problems which we'll highlight in this lecture, okay? All right, so let me give you an example of how this happens because, you know, at first you may look at that and say like, well, is that really kind of realistic? And even though I tell you it's kind of become the default setting, it's good to have something kind of concretely in mind. So what's one way that this happens? Okay. So one example, which is, you know, actually Stanford based, is that we could place sensors all over campus, okay? All over campus. And let's say those sensors read tons of information, temperatures and wind speed, all kinds of things. And so they record at thousands of locations, locations, and values. Okay, so just a huge amount of information. But, so D is, you know, in the thousands or tens of thousands, Okay, so these are like little smart dust sensors everywhere. Okay, but they only record for 30 days. But only for 30 days. Okay, so we get like, you know, n here is we get 30 samples. Now the sample we get, if you like, is a measurement across the entirety of campus. So it's like we're getting a matrix that's kind of in the opposite direction from what we're used to. It's skinny, but it's not tall and skinny. It's n rows, and then the rows are really, really big. Okay? All right. So I would just point out, maybe it's not obvious why, it will be obvious hopefully in a second, that we would want to fit a density to this. But it kind of seems hopeless. And the reason it seems hopeless is we've had, every model that we've had a parameter for every dimension. And so now there's a huge number, intuitively, a huge number of models that are out there that will all kind of satisfy this data. If we were to run something like least squares, right? If you only gave me 5 examples and you had 1,000 dimensions, there are tons of models that line up on those 5 points, right? That kind of touch that rank 5 subspace. But all the rest of them are free, so how do we pick from it? And if we try to do a probabilistic thing, it gets even worse, okay? So let's see the key idea, and if it's not obvious to you it's a problem, we'll show you something very concrete in a moment that it's a problem. So this is mainly intuition right now. This is not mathematically grounded. We'll show you the math in a second, and what will happen is you'll see our equations will just break in some fundamental way. And so our key idea to get out of this is that we're going to assume there is some latent structure, because that's the tool we're using right now, random variable, that is not too complex, and not too complex means that I can estimate it. That's really what it means operationally. And captures most of the behavior, captures the interesting behavior, right? And this is the tired maxim in this course, that all models are wrong, some models are useful, right? It's not going to be a perfect model of what's going on, but it captures most of the interesting behavior in this relatively compact way. And so we'll see at the end of this little section, we'll see a concrete generative model that builds with these building blocks and allows us to recover those parameters. That's the key idea. Okay, so let's see the first problem with why GMMs would have challenges here, and see the first example. And actually, we're going to look at something even simpler than GMMs. We're going to look at fitting a single Gaussian. Okay, so let's try and fit a single Gaussian in this situation so I can make more concrete my assertion before, like it's hard to fit models here. So let's fit one Gaussian. Okay, so the Gaussian has 2 parameters, recall, there's mu and sigma square. So how would we be tempted to compute them? So first we want to compute the mean of our data. Well, that actually seems to kind of make sense. We compute the sum here, sum over all of our data, 1 to n, right? So just make sure, let me write the data because I should have written it out. We have data points, Rn, element of Rd, just to make sure those types are in your head. Okay? This is okay. This works fine. We compute the mean, that seems fine. It doesn't matter how high the dimensions are, right? You can compute the mean and it's a sensible thing to do, right? It may not be a great estimate of the center, right? Because you may not have all combinations of the directions, but it's still an okay enough estimate. The trouble comes when we look at the covariance, and I'm going to write here the covariance in the full general form because we need to talk about the dimension, because the dimension is high, so I can't just use the 1 sigma. And if you remember, you have some expression which roughly looks like this. xi minus mu t. Okay, so that's a fair enough quantity. You can form that quantity. But one thing should cause us a little bit of pause. What's the rank of sigma? Well, generally, we've been assuming when we did linear regression and everything else, the rank was at least d, the number of dimensions. Like it was a full ranked object, right? But the problem here is that d is much bigger than n. And I've just shown you that sigma can be written as a sum of n rank 1 vectors. And if you remember your linear algebra, that means that the rank here is less than, which is always true, the minimum of n and d, which in this case is going to be strictly less than d, because n is smaller than d. That's what we're assuming. Okay? So this isn't full rank. So where does that cause us a problem? Well, we have to go back and write our favorite function, the Gaussian likelihood, and see where this causes a problem. Likelihood. Okay. So remember, our favorite thing looked like this. Sigma is equal to, at 1 over 2 pi sigma 1/2 xi minus mu transpose sigma inverse xi. Oh, there should be no xi, sorry, it should just be x. So get through this, the bottom of it, so on. Okay, awesome. why is this formula problematic if sigma doesn't have full rank? Well, there's two parts that kind of don't make sense, right? One of them is this. If it's not full rank, the inverse doesn't make sense, right? It's not even defined. And second, this is the determinant. What's the determinant? 0. Now you're toast. Because that's 1 over 0, this is now infinity. Or something like it, or undefined. No matter what, it's going to cause you a problem if you start to normalize by something like this. Okay? So how are we going to fix this? All right? So this, by the way, just to make sure that's clear, this determinant is equal to 0. Okay? Now, we're going to fix these issues. Just one second. We're going to fix these issues by changing the model. And that model is going to come out. And the thing that I want you to think about is we're going to try and make that covariance full rank. Okay? And we're going to see various assumptions that we can place on the underlying noise model. This will make sense in a minute. That allow us to insist that sigma, in fact, is full rank. Yeah, you had a question?
Yeah, I just forgot why would the determinant be 0?
Oh, because the determinant is the product of the eigenvalues, and at least some number of them are 0. Right. Awesome. Okay, so the way we're going to fix this is we're going to examine these simple models. Now, the reason, I'm going to put these models pedagogically, and why I'm doing it in this order is, the final model is going to take these building blocks and put them together. Okay, so if you were like really into the suspense of what's going on with our sigmas here, like I've ruined it for you, that's what's going to happen in about 20 minutes. But what I'm going to show you are different ways that we can get around this challenge so that we can estimate the covariance, get a Gaussian likelihood for that setting, and they're all going to boil down to ways that we kind of make sure that our covariance is parameterized by something fewer than all of the roughly n squared parameters. Covariance has to be positive semi-definite, but it still has a lot of parameters. Okay, so it's not all full. Not every matrix is a covariance matrix, but a lot of them are. Okay. All right, so let's go through it. Now, let me just recall the MLE for Gaussians, because it will make our life a little bit easier here. Oops. The reason I'm recalling this is I want to store some facts or remind you of some facts that will be useful. Now, one thing, just so you're clear, like on using this, these are just helpful things to know about like kind of computing these EM models again and again. So hopefully this is useful practice, even if you're not computing these. So remember, the way we fit these things to data looks like this. We sum over all of the data. We take the log of 1 over 2 times the likelihood, exp of, oh, sorry, there's a negative 1/2 here. That doesn't change the story. 1/2 x minus mu, transpose sigma inverse, x minus mu, and so on. Okay? Now, this is equivalent to minimizing the log, which we kind of do everywhere and expand out, which is equivalent to minimizing this. And you've seen this before. I just want to remind you where it comes from. Sum I equals 1 to n, x minus mu, transpose, sigma inverse. This is why I consistently drop the 1/2, because it doesn't matter, but it is distracting. Okay? All right. All right. Now, one key fact, which we will use again and again, and I'm just going to dispense of once, is if sigma is full rank, the covariance is full rank, then sigma u of this function here, which I'll just call f of mu, or fi of mu, is equal to the sum I equals 1, let me extend the purple blob, pink blob, 1 to n, sigma inverse xi minus u implies mu equals 1 by n, sum I equals 1n. So I apologize if this is too pedantic. If not, what I'm saying here is this is a plugin. If we know, no matter what, that sigma is full rank, then I can use this estimate for mu. Okay? So I was saying before that the average was no problem. So long as sigma is of the right form, I can always do this. And remember why. If this is full rank, I can pull it out. This is the same argument we went through last time. So ask me a question if it's not clear, because you have seen this before. And so then we satisfy from mu. We can just use that as a plug-in for everything we do later. Sure.
Why can't you only pull it out if it's from rank?
So if it's not full rank, so let's imagine that it had some null space, then it could be, then this x minus mu could be satisfied by either being identically 0, which would be in the null space no matter what, or anything that's collinear with the null space. That has like a, so if the null space is, a particular direction, then it doesn't define mu. It can be anything along that direction will be set to 0 by this, right? So it means the mean wouldn't be the unique minimizer of it, right? Cool. Yeah, it'd be 0 plus that thing. Go ahead.
Oh, so the F is the just highlighted part in the summation.
That's exactly right, and the summation. It was just so I didn't have to copy it again. Yeah, this is just exactly this. And this is the exact calculation we've seen a couple times. Yeah.
This is after heavy computation of the first line that we have done earlier, right? The second line.
Yeah, so this is basically saying these two are equivalent, right? We saw this before, that if we wanted to maximize likelihood, it was equivalent to minimizing this loss functional. I want to use that because I want to, this is a lot simpler, and it doesn't have like all kinds of like extraneous terms and things that I need to deal with. And so I want to get to the point where I can just operate on this so that I can give you some mathematical facts when I draw the pictures. That's why I'm doing it. Yeah, you could do everything in terms of the original equation. There's no harm or foul from doing that. And, you may prefer to do it that way. Cool. And we're using the fact that like the constants don't matter and all the usual stuff when we go to minimizing. Okay, so let's see our first building block. There's a picture coming. I don't know why. I think this will not pique your interest, but I'm still going to tell you. There's a picture coming that I think is very fun to draw that uses all the building blocks together, and I'll highlight for you when we get there. It's a real privilege to draw this ridiculous picture for you, and it's going to be really disappointing after this setup. So I'm very excited for it. That's like maximizes my enjoyment. Okay. So here I want to think about the first building block that we're going to draw. This is not a fun picture to draw, but it's okay. So suppose that we assume that every direction has independent and identical correlation or covariance. Okay, so if I think about the noise ball, what does it look like? I'll draw 2D here. Oops, come on, snap 2. So what this means is that our model of kind of Gaussian noise, if you think about it, so this will be sigma is equal to sigma squared I. Okay, so that means it's I, and the only free parameter is this sigma squared, which is a scalar. This is a scalar. Okay, so how many free parameters are there? Precisely 1, right? The structure is, the covariance is sigma squared times I. So what does that actually look like? It looks like I have a point which can be centered anywhere. The Gaussians can be centered anywhere. They can have arbitrary means. But their covariance structure looks like circles. Okay, that's one circle. Second circle. They should be concentric. The limitations of my notability skills. Okay? There could be another one down here. Okay, they all have the same. Okay? So you may look at this and say, so this is like the pictures, these covariances are circles. But I'm just trying to emphasize what this restriction means. And so that circle is just parameterized by two numbers, vectors, the center, the mu, and then its radius. Okay? And that's what sigma squared is. Okay? So in this situation, what is the MLE? What is the x? Well, we know mu because this is full rank. Why is this full rank? Because it's scalar times the identity. As long as sigma squared is bigger than 0, this is a full rank matrix, right? Rank is exactly n. So what is the MLE? Well, we're minimizing now over one free parameter, and it looks something like this. 1 to n, xi minus mu, except for when we take the transpose here, it's all times a scalar, so I'll pull the scalar out in front, and it'll be minus sigma squared. Okay? Plus d log sigma squared, right? So the determinant of this thing is the dimension times sigma squared. Well, it's the determinant of this thing is sigma to the 2d, and the log of that is d times log sigma squared. Okay? Determinant is a product of the eigenvalues. All the eigenvalues are sigma squared. How many eigenvalues are there? D. So I'm just saying in a very complicated, unnecessarily complicated way, this is true. Then I'm just taking the log and writing it in that form. Okay? So just for notational purposes, let z equal sigma squared. What does this actually look like? Well, it's minimizing 1 over z times, this thing is a constant here. This does not depend on sigma squared in any way, so I'm just going to call this c, plus d log z, min z. So just take the derivative. What do I get? Minus z over 2c plus d over z equals 0. And if I've done my job correctly, this is going to be z is equal to c over nd, i.e. sigma squared equals c over nd. Okay. Just to write it, to make sure it's, just to unpack it so you understand this, so you don't get lost in the weird notational pieces, this is basically what I'm saying. This is the estimate. Okay. I minus mu. Okay. Hopefully this makes sense. What is it saying? It's saying average over all of the different variances that are there. Treat them as if they're basically nd of these things that are estimates that you're seeing sigma, nd times. Average over them, and that's what you should get. So another way to describe the rule here is subtract the mean and square all the entries. Subtract mean and square. Roughly. Okay. Okay, so what do you know at this point? Oh, please.
Just a quick question. On the second line where we write the min, aren't we missing a sum over I to n in front of the d log c?
Oh, sorry. So yes, these are part of the two things. So when this comes out, this should have an nd here. Sorry. Yeah, my simplification on the fly to simplify my notes did not make sense. That's a great catch. This thing is going to be c, and this sum is inside each of the ends. And so this should be nd. Sorry about that. Wonderful catch. Awesome. Please.
What's the physical interpretation of the sigma square and the previous sigma?
Yeah, so the idea here is we have some direction. And so one intuitive way to think about this is there's some radius that makes sense. And you know how to fit a radius on any dimension, right? So you know exactly how to do this if it were one dimensional. And what this is basically saying is I collapse all the variants in all directions, and it's almost like I just lay them out in a line and average across all of them. And what I'm saying is that's not too surprising. This math is the correct way to understand what should happen. That intuition is not going to help you too much, but at least lets you type check that like it makes sense and it has the right dimension. And what's great there, as was pointed out, was this nd is just averaging over all the entries, right? Like, and the n has to come from averaging over all the entries. So sigma squared is a scalar, so it's just going to be a single number, but then we're going to multiply it times the identity. So if you picture it, it's just going to be that number repeated on the diagonal. Yeah, please.
This is the hypothetical situation where the covariance matrix is actually a scalar times identity.
Right. So yeah, so in any model is always going to be a hypothetical situation. We're always talking about what are we modeling here. And so what we're modeling here is, let's imagine a situation where this would be appropriate. It'd clearly be perfect in the case where we had noise that we knew was actually the same magnitude in absolutely every direction and didn't depend on the underlying data. We'll talk about procedures that try and make us close to that in the later part of the lecture, but ignore that for 1 minute. That will probably never be true empirically, right? For a variety of reasons. But this is a pretty good approximation. If they don't fluctuate too much, do you want to pay the expressive power of having to model all the different fluctuations in all the different possible ways, all the different ellipses that you could possibly have? And this is just saying like, if they're kind of anisotropy, if they have the even distribution, then this is an okay model. Cool. let's see let's see our second building block. There are not lots of building blocks, there are 2. Okay. Let's see our second building block. All right, building block 2. So sigma is going to look like this. It's going to be diagonal. Sigma d square. Okay. Now, what does this look like in my head? These are axis-aligned ellipses. What do I mean? Well, they may differ like this. Oops. That's pretty good. All right. So this noise parameter is still parameterized by a mean, which we know how to set. This is clearly full rank. Why is this clearly full rank? Well, because all the numbers are greater than 0. Its eigenvalues are all positive, so it's full rank. It's also, by the way, clearly positive semi-definite or positive definite because all those numbers are positive. Okay, so it is a covariance matrix. And this is what it looks like. It's basically saying that the ellipses, the errors, are not correlated across multiple dimensions. They're basically independent on each of the dimension. And so the error profile is going to look like a flat ellipse. All right. So this is basically saying I have dimensions that differ wildly, but I don't care about how often they interact. Right? That's roughly the model that you have in your head, right? Like there's a lot more variance in component 1 than component 2. That's worth modeling to me, but not at all how they interact. Okay. All right. So we're going to set zi equal to sigma I squared as above. Same thing we did above. We're going to minimize now over z1 to zd. These are all scalar values, all positive too. Doesn't matter too much. Sum j, d, j equals 1, I erase that, 1 to d, z minus 1j times xi minus mu j squared. This is now a scalar, plus log zi, okay? And this is inside, the parentheses are inside this thing. I just write it just because that's the way it should associate, okay? Oh, that should be j. If I made any other bugs. Probably. We'll get there. All right. So far, so good. What does this look like? Well, the reason I wrote it out like this, so first be clear about what we did here. This broke out per dimension. So really, this is just D independent problems. Right? So what should we expect? Well, we can go ahead and compute this thing. But it's going to look like a problem we've solved many times before. J, sorry, this J, that's the typo there. J square plus log z j, which implies sigma j square equals 1 over n, sum j equals 1 to n, sorry, j is the dimension, I equals 1. xi minus mu I square. Let me make sure I have, mu j, mu j. All right, let me write that again so that it's clear since there were a bunch of typos there. Sum I goes from 1 to n, xi j minus mu j square. Okay, so what's going on here? The thing that's going on here is we have D independent problems. That means we have D one-dimensional problems. And this is exactly the estimate that we had for one-dimensional covariance. There's really nothing else going on. There were a couple of bits here that were using the jth mean and the jth component. It's like every component was handled independently. Okay? All right, we are ready to talk about our factor model. Okay, so what is this? What is the purpose of me going through all this? One is I want you to be pretty comfortable with kind of going back and forth between, hey, what is my MLE? What does the structure I put in, and how does that change my estimate? Okay, that actually is pretty interesting. You put in the different structure, it reduces the number of free parameters, and that allows you to estimate things with far fewer amounts of data. We're going to combine that now in a pretty interesting way, which is what the factor model actually is. Our factor model. Okay? And the other reason to give this is it's an example of a more sophisticated generative model than we've typically been used to. Yeah.
Can you go back to the previous page?
Sure.
Yeah. Could you explain the graphical interpretation of this matrix again?
Sure. So in general, a covariance matrix is an ellipse. You can picture that ellipse, right, where the different directions correspond to the eigenvalues, right? And so what's going on here is that instead, because we were putting it on as a kind of on the diagonal, that means that the stretch is only on the individual axis. So like you have something that's axis aligned, like the major axes have to be aligned. So when would that be a reasonable model? It'd be a reasonable model if you thought like there are different amounts of spread or different amounts of variance for every dimension, right? The previous model said all the variance in any direction was effectively the same. There was one parameter. So that's why it was a circle. Now it says there's different amounts in different directions, but I'm not going to model their interaction. In contrast, a general covariance matrix can tilt and say like, no, the principal direction, which we'll come to when we talk about PCA, is in one direction. And I'm a little bit setting up for those kind of calculations later is why I draw these. Right, so this says I don't care about interactions between the features, very roughly speaking.
Okay, but basically it's saying that the spread in each direction is overall the same.
No, they're different. There's a different parameter for everything. So there's sigma 1 and sigma 2 are potentially different numbers. Right, that's why it's an ellipse rather than a circle. If they were all the same, it would be the circle. Cool, awesome. Fantastic, so let's look at our parameters. There are going to be a lot of them, but it gives us a more interesting generative model to look at. And if you kind of wade your way through this, you understand EM, you understand how these models work, and hopefully it gives you confidence that you're not looking at just one setting. Okay, RD by D. It's going to be a diagonal matrix. Okay. All right, so let's see the model. And then the world's, I don't know, it's not really that remarkable a picture, but I enjoy it. All right, Px of z. So we do the usual thing here, that it factors as a latent model. This is exactly the same since z is our latent model. Okay. By the way, mu is in RD. This is a linear transformation that we're going to learn. This is a diagonal transformation, hearkening back to what we just talked about. And here is the way x is distributed. Z, start with z, is going to be some 0, 1. So it's just some random noise vector in Rs for some s smaller than d. Okay? This is this, I'm going to call this s because I want you to think about it as the small dimension. So the latent structure is small. We want to pick the latent structure to be much smaller. D is 1,000, 10,000, a million, a billion, something like this. We're going to pick S as saying there's a small subspace that characterizes and classifies all of its behavior. That's like the compression. That's the bottleneck. Then we're going to say X, and I'll walk through this slowly in a second, is this expression, epsilon, okay? All right, so the model that generates X, and I'll write this more compactly, X is not just centered at the origin. It has some mean. Z is going to be mapped from the small dimension to the large dimension by a transformation that we're going to learn. So imagine the sampling procedure is Z gets selected. If you knew lambda, you would map it up into RD. You'll shift it by epsilon, by mu, the mean that you're going to learn. And then you're going to put some epsilon noise here. Okay? All right. Now, let's get the model for these things. So epsilon is going to be normal. It's noise, so it'll have 0 mean, and it will have phi as its parameters. This implies, by the way, now we have all the information, we could also write X is distributed as n mu plus lambda z plus phi. Please.
Oh, like, what is the physical meaning of S and lambda?
Yeah, great question. So let me just say, so this is, I just want to annotate this as the mean. So I'm going to draw what goes on this for an example in 1 second that will answer this a little bit better than I'm able to, because once you see what's going on. But the intuition is you're going to sample in the small space. You don't know where it is. That's your latent variable. That's your link to clusters. That's the thing that you say, like, I don't know what it is, but I know there's a small structure lurking out there. Then lambda says, from that small space, I'm going to go into the big space, right? The D much higher dimensional space. And lambda, I'm going to learn that transformation that says, how do I go from the small space to the big space? And then the big space is going to be the actual dimensions. So imagine I was actually had these sensors, and they were getting temperature readings all over campus, and they were getting wind readings all over campus. Well, clearly they're correlated, right? Like if I put a bunch of sensors all in a line, they're not independent readings, right? There's some sensor, and then there's some map that tells me from the reading that I got, what should I expect at all the sensors with like pretty high probability. Like you could imagine such a map existing. And so the lambda is that map that goes from the kind of low dimension to the high dimension. We're just doing it in a very abstract way, and we're not specifying what those dimensions even mean to start with, right? Please.
This could be an end rate.
You probably don't want to set it greater than n for a variety of reasons, but like, yeah. Like you'll see in a second what the conditions are when you go to solve it. Great question. There's some condition that's lurking there. You need to be able to estimate. There's no free lunch, right? But yeah, it's going to be smaller than D, right? D is 1 billion and n is 20. There exists some s where we could potentially solve this. That's the way to think about it. Not we can solve it for every s. Awesome. All right, so let's see an example of this whole thing where D is equal to 2. So not that high a dimension, but like good for drawing. S is equal to 1. And n is equal to 5, okay? And our model is x mu plus lambda z plus epsilon. And let's see how the forward sampling works. So how does it work? 1, we generate z1 to zn from n01. So what does this look like? All right. So here's 0, and we get, let me see if I can draw this nicely. We get a bunch of samples. So maybe, oh, here's 0. Let me mark down 0. 0. Oops, that didn't look right. Here's 0. So here's let me draw the density actually. So the density looks like something like this, right? This is the Gaussian, in loosely interpreted artist rendition of Gaussians. Then what I'll do is I'll sample. So maybe I'll sample this point first. And I sample over here, sample here, sample here, sample here. Those are my 5 points. How did I pick them? I don't know, I sampled. So like this is Z, oops. This is Z1. This is Z2. I'm not remembering the order that I did it, and it doesn't really matter. Z3, Z5, Z4. Okay? So I just generated those in 1 dimension. All right? Now, 2, what happens? So now so far I've done this piece. All right, so this character is handling this. Okay, now I map by lambda. So let's suppose we've already learned lambda. So lambda is equal to 1, 2. So what happens next? Now we're getting fancy. Take this, copy, paste. So now we need the x-axis back. So these things get mapped. Here's the line 1, 2, which goes to the origin. Okay? What happens? So then these are all mapped onto the line. Oops, it's a little small, but good enough. This one's mapped all the way up here. Okay? Down here and down here. Okay? So this point, for example, is this point is lambda z3. This point is lambda z2. So far, so good? So this whole thing, now we're in the high dimension. So we've gone from our small dimension up to the whole dimension of all our sensors. Think in your head dimension 10,000, not dimension 2. Okay? Now, 3, we add mu. What does that do? I'm going to put that in green. That's this piece. Copy, paste. Mu, let's say, is this vector here. This is mu. We add mu to everything, and that translates all our points now by mu. And there's one off the screen now, over here somewhere. Okay? This point is, oops, mu plus lambda z2, right? It's this point translated by mu. Then 4, we add epsilon noise. And this epsilon noise is full dimensional. So I'm going to make this in purple. This character here. Right? This is the equation that we're dealing with. What happens next? We get some purple stuff, and it goes like this. Oops, make it a little bit thicker. It goes like this, goes down here, goes over there, but it's full dimensional noise. It lives in a d-dimensional space. And that is our final expression. So for example, this character here, oops, this character here is mu plus lambda z2 plus epsilon 2. And epsilon 2 is the noise. And notice the noise is in different direction for each one. Right? So I want this is in, by the way, this is in the high dimensional space, in dimension D. Okay? So what's going on here? We were talking about that sensor and temperature example. So just kind of walk through. The z's here were generated in one dimension, let's say. That was the underlying true temperature that you were going to see, several samples of it, maybe at different times of the day, right? Because z was collected at various different times for different data points, right? We were collecting it many times in the day. Then we mapped using lambda to say like, oh, if the temperature were kind of the true temperature, or some hidden temperature, was 50 degrees, then all of the other temperatures that are nearby are going to jiggle in a predictable amount. Predictable amount meaning lambda maps them from wherever their value was to the high dimensional space, right? But the problem is there's still some residual noise. That fit may not be perfect, right? We can't predict things. Noise means like just stuff we don't want to model. And that's where this purple comes in. That's the epsilon jitter that's in the high dimension. Does that make sense? And that's our underlying model. And the data we see are the purple dots. So the data are the purple dots. That's what we actually see in the data are the purple dots. Okay, just to make sure, it's x equals mu plus lambda z plus epsilon. All right, please.
Is it assuming that the actual, so even though the sensors give us data of dimension D, which is really huge, but are we assuming that the actual thing that we want to model, like say the actual temperature of the dimension is much smaller than that?
That's exactly right. So much smaller than D. So what we're assuming is we have, again, I think the illustrative example, which will get you most of the way there, is I put 1,000 temperature sensors in a row. So I get 1,000 numbers every time I measure them. But if they're all close enough, it feels like there should be one temperature, and they're all kind of, there's a mapping from them. That mapping we're going to learn. That's what lambda is. Lambda takes us from that one true temperature to our guess at all the different temperatures. But we're aware that that's imperfect. And since we're aware that that's imperfect, we also allow ourselves some error, epsilon, in each one. Maybe one temperature sensor is damaged, it's dirty, someone walked by it, someone blew on it, who knows? That's what epsilon models. Does that make sense? And so it's the small to big. And that's what allows us to learn this, because we're saying, although there's this huge amount of free parameters, we only have a little amount of data. We have to make some compression. And so that's what the latent structure is doing. Okay? Please.
I have two questions. So first is that here essentially we are assuming the major assumption of ours is that this is something close to it's a linear form of data, just having a bit of noise in it that's really distributed.
Yeah, so here we're making an assumption, that's right. We're making an assumption that there is a small distribution, there's a distribution that's low, and that there's a linear map up into the larger space. You could imagine more sophisticated models that had a learnable nonlinear map into the larger space. And there are various reasons that may be hard in limited data regimes. You may not have enough data to learn that piece.
The second question pertains to S. So here S is equals to 1.
Right.
What would happen, like, and therefore it's easier to imagine what's actually happening. But what would be the case when S is not equal to 1?
Yeah, wonderful question. And we'll get into this a little bit in PCA too. And sometimes they're interpretable, sometimes they're not. But let's imagine when we come back to it, we'll have this language of principal components in about 15 minutes that will may be able to give a little bit more precise answer. So I may punt there in a second. The idea is that S captures kind of the important directions of variation. So like if you imagine the temperature sensor, so I have temperature and I have electrical current that are there. And maybe there's also some, wind thing. And if I combined all three of those, I would get a really good estimate. But I need an estimate of like the wind speed at a location and all the rest. Then S would be some mixture potentially of those kind of, true directions that are out there. Now, often that story that we tell ourselves is difficult to verify because we don't actually get to see the latent variable. And in fact, we can get away with making a much weaker assumption, which we'll make in PCA, which is basically that there exists some low-dimensional space that captures our system. And that turns out to be a fairly robust kinds of assumptions. It's not that we know there are only these three parameters. If we knew it was wind and temperature and we were just learning the map, we would just feed that in, right? We would just measure that and feed that in. We're hypothesizing that there exists this small bottleneck, and that's what's going to allow us to learn in this setting. And to me, that's the really rich pedagogical reason to teach this is like it kind of forces you to think about like what can you really recover. This is more of a statistics view of this part of machine learning, but what can you really recover from data? Right?
Okay, so you essentially kind of through S, you kind of dumping down D, right?
Yeah, you're just saying there exists something small underneath.
Oh,
You got it right. Please.
Do you do this for do you create this transformation for every data point?
Wonderful question. So here, lambda is across all the different data points, this transformation. So if you look at like this notation here, like you'll see that Z is generated once per data point. So there are n of those things, n latent samples. There are also n latent noise samples. Those are different for every data point that are there. But lambda is shared across all of them, as is mu in the model. Now, if you knew something, like you knew there were k clusters, and there were k different maps, you could potentially fold that into your model, or k different means. But this is the model we're looking at now. Doesn't necessarily need to be that way, but for now, that's what we're looking at.
One more question. From my understanding is that we start from Z and then we work our way from, like we generate Z first,
Right.
then work our way to the data. But how do we estimate like S, or do we start from?
Oh, great question. I get exactly what you're saying. So when we went up here, remember, in this model, so one of the messages is we start with this model. And in the generative way of viewing things, like the real reason I like to keep this in the class in a very fundamental way is because like it forces you to think about what is actually in the model. Like when you see the EM thing, it's kind of in a similar situation where you're like, oh, there's just this one kind of hidden aspect to it. This Z is latent to us. So the part of the model is you pick S because it's one of the parameters. So you have to tell me ahead of time, I want you to model with a size S model, and then you run this whole thing forward. And then our goal is, among all those things that could have gone forward, what are the most likely settings of the parameters in that model? So we're not learning S in some sense. We'll talk about in PCA, when we're learning a linear subspace, we can effectively look at a particular measure and see if adding one more dimension would be there. And I'll come with some caveats. Great questions. Awesome. All right. Okay, so we need one technical tool to make this whole thing go. Let's do some technical tools. I'm not sure that these are super useful to prove here, but I will happily point them out to you as we use them. All right, so here we're going to use this notation. You probably have seen this before. If not, don't worry, we'll review it right now. X1 is an RD1, X2 is an RD2, and D equals D1 plus D2. Okay, so this is just a nice way of partitioning. This is because we're dealing with something that's linear, and we can have this kind of block structure. Okay, we can also do this for matrices, and that will allow us to state some theorems just a little bit more concisely. Sigma 1, 1, sigma 2, 1, sigma, oh no, so this should be 2, 1, sorry. I don't know why it's backwards. 1, 2, sigma 2, 2. Maybe okay, I hope I didn't do something notes. All right, so this is D1, this is D2. This is going to be D1, and this is going to be D2. All right. And sigma ij, if I've done my job, should be, oh, it's going to be R. That's why I did it the backwards way. Yeah, that makes more sense. Sigma ij is going to be D J, or hold on. Let me actually change the numbering just to make it consistent with the notes. Sorry. This doesn't really matter conceptually, but just to explain it. Okay, 1, 2. All right. So the point is I can factor this in some way, and it makes sense to multiply a matrix in an obvious way if it's compatible with the blocks. So like if I multiply this matrix here, x times sigma, I can write it in terms of these blocks. Hopefully that's clear, right? And it would be sigma 1, 1 times sigma 2, 1, and that would be what I would want to put there. Okay. All right. This is a very widely used notation, and it's going to let us state 2 facts about Gaussians that are really helpful. If you're not familiar with it, just take a look at it and see. So first one is the marginalization identity for Gaussians, x2, px1, x2. Okay? For Gaussians, this has a nice form. This is not true in general. This is why we love Gaussians so much, really, or that it has this really nice form. Px1 is going to be equal to a normal, or it's going to be distributed like a normal, mu 1, 1, sigma 1, 1. Okay, this is called marginalization. It basically means I can grab the mean that I want to grab and the covariance I want to grab when I marginalize them out. And this is because Gaussians have this nice property about being independent in these directions. Okay. This is a much nastier statement, fact 2, which we will use. Px1 conditioned on x2 is also Gaussian. Pretty remarkable, if I'm going to be honest. Like, not a lot of distributions are closed in this way. What I mean is closed, if I do an operation like conditioning, do I get back the same distribution? That's actually pretty unlikely, but Gaussians, it happens. And so again, it makes some of our calculations easier. This is marginalization. This is conditioning, okay? And so what are these 2 values? This is going to be equal to mu 1 plus sigma 1, 2, sigma 2, 2, and I'll put up notes and you can look and see the notes do this, x2 minus mu. This looks super mysterious. It's actually not, but it's not probably worth going into too much detail. If you remember your matrix inversion lemmas, if you don't, again, don't worry. These are not super conceptual, like important details. It's just how this works. You can go through, and I can gladly upload a proof for you if that makes you feel more solidly grounded. If not, you can just use this. Okay? And these formulas, when I say it's not conceptually important, you may think that's a cop-out. Maybe it is. But really, the reason is it doesn't matter to me because there's only one way these formulas make sense. The types all work out. You have D1s and D2s, and you're multiplying them in the right way. Otherwise, the formula is wrong. Okay? Okay? So this is the matrix inversion lemma. If that helps you, great. I'm happy to prove it. The thing that I care that you take away is that we have these formulas, and we can use them later. So when we do a conditioning step, we can use them. Okay? When we do a marginalization, we can use them. Okay? And this is, I realize this is like impossible to appreciate at this moment probably, but it's relatively rare that we can go from a distribution, condition on it, and get back a distribution, right? That we have the same, what are called sufficient statistics. But it happens here. Just don't expect that in general, please.
So I think through both of these facts, we are assuming very deep dependencies between not just within different data samples, like between data samples, but also within the features of the data samples, right?
So I wouldn't look at it through that lens. These are mathematical facts about Gaussian distributions. These have nothing to do with data per se. This is just true about any kind of wild Gaussian that you would want to meet, and so you would use it that way. We are going to show in 1 second that crazy model I just showed you can be written in kind of a nice way using these things. So how do we use it? So remember we have 2 variables, n, 0, sigma, right? All right, and this is since epsilon of z, the expected value of z is equal to 0, and the expected value of x equals mu. Now, we don't know sigma yet. We just say there's a covariance out there. We're going to derive what it is in 1 second. But the point is that whole factor model basically boils down to some gigantic Gaussian. And that's going to be really helpful to us. The problem is, like, this form, like, this is going to be data. This is going to be hidden. And so we're going to have to deal with marginalization and conditioning and all the rest of it to be able to recover it. But the point is we can write that model super compactly. Now, I think if I wrote that first, probably you wouldn't be super happy. Maybe you'd be really happy. I don't know. Maybe you're happy folks. Sure. Which line?
This one.
So, and again, you can type check these things. Just make sure it makes sense. It's got to be a D by D map or an N by D map for everything to make sense and all the types checked out, if there are typos, which I'm sure there are. Okay, so let's try and, now our job is to try and figure out what is sigma. And by the way, this is kind of remarkable. Like, we went through this pretty elaborate discussion about various different models, you know, how the model worked. And lo and behold, it's just some nice Gaussian. What is the, so this is the, so it's because it's block, 1, 1 is the outer product of z with itself. Well, what's the outer product of z with itself? It's just the identity. Why is it the identity? Because that's the way we sampled. Remember, we sampled in a low space. This is using this fact, oops, is using this fact, right? So E expected value of ZZ transpose, that is exactly I. Okay. What is sigma 1, 2? Well, it's going to be the expected value of Z times X minus mu transpose. What does that actually equal? Well, that's going to be the expected value of Z transpose, right? So X minus mu equals what? It equals lambda Z plus epsilon, right? That's just the model. I just subtracted off the mu on both sides. So it's going to be Z transpose, lambda transpose, plus E Z epsilon transpose. Now, these two things are independent. Oops. Z and epsilon are independent, so boom. This goes to 0. This we just concluded, this we just concluded was the identity, so this equals lambda transpose. And sigma 2, 1, oops, I'll write in the other color. Sigma 2, 1 equals sigma 1, 2 transpose. Because it's a covariance matrix, positive, it's symmetric. Okay. The last one, or you can just compute it, take my word for it, but you don't have to take my word for it, is this one, X minus mu transpose. We just use this formula again. That's going to be the expected value of lambda z plus epsilon transpose. We have some multiplications to do. We know that all the cross terms with epsilon are going to cancel out. So this is going to look like, and this will maybe look mysterious, so maybe I'll go a little bit slower here than I wrote in my notes. Epsilon transpose. Okay, so why? Notice you're going to have an epsilon times this term in the transpose, but the expected value of epsilon is 0. So those cross term is going to cancel. The only one that's going to remain are this one and this one, where the epsilons are multiplied by itself. So both cross terms fall away. What does this equal? Well, we just saw this is a random variable. This is a deterministic parameter of the problem. This is going to be lambda transpose. And this is going to be plus the phi. Why did that happen? This phi is the model. Sorry for the scrolling. So please avert your eyes if it makes you nauseous. It's this character. Sound good? So let's write the whole model in summary. And again, you can check the types on this thing. Make sure I didn't make some silly mistake. Okay? And we're good. So now it's in this nice Gaussian form, and oh my gosh, I claim you already know how to solve this. E step, what is Qi of z? I won't go through the whole EM algorithm. You remember, is P z of I given xi and theta. What do we use here? We only have two rules. Yeah, use the conditional. That's all we got. Use the conditional. M step. Well, it's a normal distribution where we filled in the x's and we're marginalizing out after seeing the x's that are in there, or conditionally on the z's. We have closed forms. You already know how to do this. Okay? So what is the summary here? We saw here this factor analysis structure that allowed us to have a lower dimensional space, had this elaborate kind of sampling and moving around, pretty wild set of generative models. And it basically boiled down to a one-liner to shoehorn into the EM algorithm. We had to use some fancy, tricks with how you deal with normal distributions. If you didn't use those fancy tricks for normal distributions, you would have to do some empirical extra work, right? You'd have to understand if I had a distribution that looked like blah and I wanted to marginalize or condition it, what would I do on top? Okay. Yeah, please.
Sorry, I'm not sure I really understand what you meant by we have closed forms for the M step.
Oh, because once we have this, these are just, so think about what happens once we have the estimates for the z. Then it's just conditioning on the z's and removing them, and we know how to estimate the parameters of this becomes just a standard, oops, where's the formula? Sorry for the mad scrolling. The crazy scrolling is here. Once you know z, you have a guess of z, then this is just fitting a Gaussian with an unknown mu and sigma. And you need to figure out what the sigma is that you're fitting, but you know how to do that. So I guess this is something we've done, maybe K lectures in a row. And it is, I agree with you, it is abstract and weird that falls out. And I want to say it in that abstract and weird way so that you're not afraid of it. Because you're going to, if you want to go into these things, you want to use these things, it'll look very strange. But once you get it in that form, it's just kind of a plug and chug kind of mentality to get all the results from things you already know, derivatives you already know how to compute. Cool. Ooh, go ahead.
Why do you write the sigma components as expectations when you roll it up?
Oh, so that's just the definition of covariance. So because I know the distributions, I want to compute what sigma must be. And I'm just trying to tell you, the reason I wrote it that way is to tell you there's nothing else going on. In the model, I'm just computing the expectations. I know the covariance of the individual objects. And that is telling me that I can write it in this form. Yeah. Cool. All right. Let's use 20 minutes to do PCA, and we should be in good shape. All right. PCA. All right, so PCA, I'm going to draw this little diagram to explain where we are. Principal component analysis. So we looked, I want to fill out this table. You say, why do you want to fill out the table? I don't know, it's just how I do it. I like that it fits. Also, you should know it, it's an important algorithm. It'd be weird if we didn't teach it. Although probably a bunch of you have seen it before. If not, don't worry about it. So one of the things that's inside machine learning, which is really kind of interesting historically, I won't bore you too much with the various tribes of machine learning theory and how we got where we got and who fought with whom at which conference. Although it's kind of funny because it's so bizarre. But there are kind of two schools of thought of doing machine learning, and at a kind of a broad level. There's kind of the Bayesian school of thought, which is everything should be written down as a probability distribution, maximum likelihood. We write these priors, we use conjugate priors, we kind of crank through the model, and we have this forward story. And then there's kind of another camp that's kind of more the frequentist style world, just from the stats side, that was we don't want to use probabilities, we just want to have these kind of nice estimates. They also like maximum likelihood, they also like Bayes' rule, but they differ in some ways of how you approach modeling and what a valid model is, how you know to trust a model, okay? Doesn't matter at all. The point is, almost everything in machine learning has kind of these two different approaches. And I'll say at one point in my career, early in my career, I built a system which was very much in the probabilistic camp, and then became kind of disillusioned with it and moved to doing something else. But there are merits to both approaches. PCA is what we're going to talk about, so that's just historical context. I just want you to know there are many ways to model a lot of these different problems, and we're going to talk about this one here. And I want you to explicitly contrast it with factor analysis, which is the probabilistic version kind of a PCA, in the same way k-means and GMM have a parallel structure. Okay? You saw k-means, we did GMM. They had a nice kind of rhythm of how they were solving the underlying problem, so it was nice to put them together. These don't have that nice rhythm, but they have something else that is nice to see. All right, so let's see PCA. Please. Oh, so. Okay, so we're going to be given pairs here. And this is kind of a weird example, but it's something that makes hopefully the main point clear. Okay, so imagine someone gave us a data set, and this data set had a bunch of cars on it. And the cars are going to be rated on like kind of highway, miles per gallon, and city. Okay, and these are gas cars. These aren't electric cars. Okay, so they're kind of scattered all over this. Okay, and I actually went and got the real data. It's not that interesting, but there's a couple that are substantially better, substantially worse than the line. Okay. Now imagine these cluster up here just to give you kind of complete the story. These are maybe hybrids. Oops. These are hybrids. Maybe these are SUVs. They have bad gas mileage or trucks or something. And these are economy cars. I don't know. Okay? Clear what the visualization is saying? Okay. So we ask a question, which at first seems kind of strange, but it's a question we could ask nonetheless. What does it mean for a car to have a good miles per gallon? Now, some cars are going to be better on the city, some cars are going to be better on the highway. We come kind of like a single direction or single kind of way that says, what is the component of principal variation, right, for good miles per gallon? And that's kind of what we're trying to ask. And by the way, PCA is typically employed in these settings when we don't know too much about our data. We want to visualize it in some way or get some understanding, right? Modern methods kind of incorporate a lot of its ideas, so you don't need to run it usually as a standalone ahead of time anymore. Like they worry about these features and things, but it focuses on one thing I really think is great. So how do we deal with this, all right? So the first thing we do is we take our data in the PCA worldview and we center it, okay? Okay. Now, what does it mean center? We compute mu, which is equal to 1 by n, sum I equals 1 to n, xi. And then we subtract mu from every point here to get the center of the data set at 0. Okay, it should be balanced in all ways. This is just to make sure that the scale, the raw numbers don't matter, because we're going to talk about geometry, and also we're going to use some ideas from linear algebra, and linear algebra likes things that go through the origin, right? We like linear maps go through the origin. So we want to the origin has a special role in linear algebra. This is still highway. This is city. Okay? Now if I look and I just eyeball it, roughly speaking, it feels like the component of variation is something like this, right? And what I mean is if I look along that direction, that tells me the more I go along that, the better the highway model is. There's some variation that's around that, but that's good miles per gallon, and below as you go, those are slightly worse. So along this line is kind of the principal direction of variation. It doesn't capture everything, right? There's this character way over here, there's some character way over here. This is an automated way of kind of denoising those data sets and other things that I'm looking at. And so what we'll talk about is this direction, mu1, which will typically be a unit vector, is a component of principal variation. Okay? This is very intuitive. I'll define it formally in a second. U1. Okay? And if I look, I can still describe all my points. This is just linear algebra by something that's orthogonal, and I'll call it U2. Okay? Now I'll construct U1 and U2, because I only care about their directions, to be unit vectors. Okay? And so you can kind of think about U1 as how good is the mile per gallon, and U2 is kind of explaining its first variance, right? Like it's the first, if you thought about it as probabilistic, it would be like the first direction that they vary, a car varies, and then like what's that second order effect? You can imagine doing this in higher dimensions, all right? Formally, one second, we can write xi equals alpha I1 times mu1 plus alpha I2 mu2. And these are scalars. Okay? This is just linear algebra. Please, go ahead. You had a question.
How certified is the principle?
Yeah, we're just eyeballing it for now. I'm saying that like looks roughly correct. We're going to find, how do we find that line in just 2 minutes, 5 minutes.
So like how can we tell that by visually?
So let me, once we write the definition, let's come back and then hopefully your intuition and my intuition will be a little bit closer, right? But yeah, that's a great question. You're thinking exactly the right way. Why is that the right line? Why is this maniac drawing that line, right? Now the thing is we may only decide, by the way, to use this as dimensionality, we may only keep this component. Okay? Because it explains more variation. And that's going to be how we define it. Variation. Ooh. Okay. So what we want to do here, just so you're clear, so here I drew it from 2 to 1, just as I was drawing before, but think about if I had thousands of dimensions. You can't possibly visualize thousands of dimensions. It's really tough. And I want to get it down to say, 2 or 3, or 5 or 10, right? I want to find those principal variants, okay? And so PCA also functions as a dimensionality reduction method. So here we show just a 2-dimensional plot, but imagine I gave you the cars have thousands of numbers, and you want to get a very succinct description of them as just 5 numbers. Or I gave you 10,000 sensors as we were talking about before, and you wanted to figure out, give me 3 numbers which really describe every different individual sensor and its variation from that number. It's very similar to factor analysis, right? Like it's looking for that low-dimensional subspace that you want. In fact, it is formally a low-dimensional subspace. It is a dimension of dimension 2 or 3 or k underneath the covers, and we'll come to that in 1 second. Okay? So at this point, this is intuition. You should have more questions than answers. Let me state the algorithm that we're going to do, the pre-processing that we're going to do, and then you'll see why some of these variation things are. Please go ahead.
I think what you're ultimately proposing is that yes, Xi has the D number of principal components, but some, like most of them are noise except for the initial 2. That's what are you saying?
I'm saying, great question. So imagine I gave you these x1 to xn that live in some high dimensional space D. Then what I'm going to try and do is find a smaller number of directions, but those directions are not necessarily aligned with the axis, which means they're not like component 5, 7, or 9. There's some mixture of all of them. And so U is not aligned with an axis, right? It's some mixture of the highway direction and the city direction. And I'm going to find that direction, and then I'm going to say that's the direction that the data set varies most in. There's the most spread in. So I want to keep where you are on that line. I'll project you on that line. Then maybe the second, the third, and that's going to be like a third kind of, a 3 numbers that best capture you in the data set if you're an individual data point.
And you consider that to be noise?
Not noise, but I'm just not modeling them. Yeah, please.
I guess what happens with the 2 variables have quadratic relationship or like instead of the relationship shown here.
Yeah.
How does it capture the direction?
Wonderful question. So we'll come back to that in a little bit. Effectively, what we're going to do is we're going to capture some variation that's there. So there may actually be some of these hidden correlations that are underneath the covers, and we won't model them well, or we may only model them well in different pieces of data. There are methods, if I know that there's a nonlinear relationship between a lot of the different elements of data, that like I can capture. Here we're assuming there exists a linear subspace, and that's a fairly robust assumption. So people do use more advanced techniques like TSNE and UMAP, which do have actually the assumption that there's some very compressible nonlinear map that explains what's going on. But PCA is kind of the first and the cleanest to describe. Yeah. Awesome question. Okay, so we center the data. By the way, I'm going to review this in 1 second. I'm just trying to write so we can get through this. Mu, we know what it is, 1 by n, sum I, 1 to n, xi. Okay, we may need to rescale the components. Why is this? Well, what if one component was miles per gallon and another was feet per gallon? They're just different by a factor of 5,000. There'd be a lot of variation in the feet per gallon, right? Not the miles per gallon. The numbers would be different. So not only do we want to like center them and get them both centered around 0, we want to rescale them so that they have exactly kind of the same width. And what we'll do is we'll just divide by the variance, by the sample variance, right? In that direction. So that all the numbers are kind of like roughly normally distributed, you should think. Okay? So we're going to assume that the data are pre-processed. If you actually do this method, you should do the pre-processing. So let's see PCA as an optimization problem. All right. Oops. Monkey business. I'll live with it. Okay. All right. So here's what we're trying to solve. And this will get back to some of the questions that were asked about, hey, why do we think this is a principal direction? Okay. We need a little bit of math before we can make that precise. X. Okay. So what we want to solve, right, what we have is we have some direction mu1, we have some other direction mu2, which is orthogonal. This is mu1. We have some direction mu2, which is orthogonal. We have, these are unit vectors, mu I equals 1. So unit vectors. And they're orthogonal. Mu I dot mu j equals 0. Or equals delta ij. Sorry, they're orthogonal. Okay, so how do you find the closest point on this line to x? Well, this line, just to be clear, can be parameterized as t times u1 for t element of R. Right? It's just a line, one-dimensional line. And so to find alpha, how do we find alpha above closest point? That's the following expression. Alpha 1 equals the argmin over alpha of x minus alpha mu1 norm square. Okay? All right, so hopefully this makes sense. If I want to find the closest point, intuitively, it should be on the line that's orthogonal here. It's not a very great drawing, but that's where it should be. It should be projected onto this line. And we can minimize over the whole line by minimizing over alpha. We do the standard thing here. We compute the derivatives, we multiply it out. Right? So this is equivalent to, when we multiply it out, argmin x square plus alpha square times mu1 square minus 2 alpha mu1 dot x. This is argmin over alpha. This doesn't change. This is a function of the input. This is 1. So when we go to compute the derivative, what do we get? We get 2 alpha minus 2 ui 1 dot x. Okay? Or, said more simply, alpha equals 0. Right? This is the gradient with respect to alpha. So alpha equals mu1 dot x. Okay? This is saying the dot product in this direction tells us exactly the closest point. Okay? This is just differentiating this expression with respect to alpha. Okay? All right. Now, you can generalize this to any set of directions, orthogonal directions. So if I have mu1 to mu k element of RD and x element of RD, how do I find the closest point to the subspace spanned by mu I? Here we're going to use the fact that mu ij equals delta ij. Well, it's going to be the following. Argmin alpha 1, alpha k, x minus sum k equals 1 to n, or sorry, j equals 1 to k. Alpha j mu k. Now expand that out again, exactly as we did before, and you'll see that alpha I is equal to mu I, or ui, dotted into x. Okay, this is the inner product, if you like. Okay? we call this quantity x minus some alpha j uj, sorry, this is uj square to k. Okay, the residual. Okay, so we have everything we need. Rushing a little bit here. But so the point I want to make is if you have a subspace and you want to find the closest point in that subspace to x, that's the same as minimizing over all the possible directions in the subspace. This distance squared makes the computation easier. Then alpha I, if you solve it, is going to break apart. And the reason it's going to break apart is when you multiply it apart like this, you're going to get products of mu I and mu j. They will all go away. So all you'll be left with is a bunch of the alpha i's and alpha j's that are multiplied in exactly the same way as the 1D case. And you should check that. And this is, if you're rusty on this, this is from your linear algebra class. Okay? And I'm super happy to write it out in more detail if that confuses you. But for now, hopefully we can just move through this. Okay? This thing here is the residual. That says, how close am I, what's my distance from x to the subspace? And that's going to feature prominently in what we do next. Please.
The subspace essentially approximates this whole distribution.
So what we're going to try and do is we're going to try and find a low-dimensional subspace, and I'll describe how we're going to do it next. And PCA, when we're talking about what's the principal component of variation, we're going to search across all the directions when we're looking for the principal component. And we're going to say which one of them has this, for example, there are two ways we can find PCA, but has the smallest residual. Or, what will be equivalent, maximizes the amount of alpha, the amount we projected onto the subset. Okay, so there are two ways you can do this. So we can find PCA by, one, maximizing the projected amount. That means trying to make alpha as large as possible, right? So if you give me a subspace, which is a section of vectors, I can compute the alphas by solving this problem. I want to compute something so that, a direction, so that for almost all the data points, my alphas are as large as possible. So getting back to the earlier question about why did I say that direction was the principal component of variation, is because if I put it in that direction, I was kind of explaining the most, and the residuals, the errors, were small. Dually, these residuals for every point are as small as possible, and we're going to minimize those in 1 second. Yeah, go ahead.
So, didn't we just normalize the data as a pre-processing step?
We did.
So wouldn't that have been residual essentially the same on that one?
Awesome question. No, not necessarily, right? Because, for example, think about even if we normalized it, there may be one direction that explains, for example, the temperature, how far it is away from the heat source, back to my 1,000 temperature sensor example. And there's one direction that explains that, but there still could be variations in other directions that are not captured by any other process, and so they would be orthogonal to that. So it's not necessary that even though all the directions on average are normalized, that for any particular point, like if there's a correlation, would be the same.
Okay, so we actually normalize all the axes with the same scale.
So all the axes are put into the same scale by taking each individual component and computing its sample variance. Yeah, multiplying by a diagonal matrix, please.
When we're taking alpha, how do we take the alpha? Is it the distance between the line and the point, orthogonally, or is it just?
Great question. So here, alpha is basically t. So it tells you how far along the line you're going to go. So alpha is constrained to live on the line. So when we minimize over alpha, we're minimizing its coordinate along the line. And that's well defined, right? There's a closest point here, right? We know that kind of intuitively from, undergrad, whatever geometry we took, right? Like that there's a closest point. But this proves it, right? Awesome. Cool. Please. Yeah, so it's either you want to capture as much of your data as possible, and in the linear case, it's either you want to capture as much as possible or minimize the residual, or turn out to be equivalent. Because here, if you look at it, because these are unit vectors, making alpha j's bigger, like if I had two sets of u's, and I'm comparing them, if the alphas are bigger for this one on average than for this one, then that says that they capture more of my data, right? Because they're a projection. The alphas are defined by the u's. Yep. All right. So let's find the principal component of direction, right? So what this boils down to, I'll just do one of the methods, the maximization one. You have to do the other one in your homework, by the way, so it's one reason to pay attention. Is this. It says, look over all the directions. Oh, sorry, you. Okay, so it says, look over all the directions that are out there, dot them into the data set. This is alpha, right? This is the alpha we were just talking about. And try and maximize the one that captures most of it. So if you imagine me sweeping that line across the earlier data set, where we were looking here, right? Here. And I'm sweeping that line here, 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 all from the origin, sorry. Go away. Here, here. Clearly this captures much more, the alphas are much larger than they are here. Right? Just take the dot products. Right? Because it's just projecting onto a relatively narrow band. It doesn't capture as much spread. I want more spread, right? It's quadratically more spread. Okay. So how do we solve this question? Here, well, we need a couple of facts, okay? Maybe we will pick this up in a little bit. Yeah, I think that's probably best. So ask me any questions about particularly this spot. We'll come back about how to solve this kind of equation in a second. Any other questions about this piece? Yeah.
Could you go back to the first point? So essentially, like this point only, that's what we're trying to do. So what you, by maximizing projected subspace, you're just trying to ensure that whatever UIs we choose, out of initial ones,
Yeah.
So maximum of the data points, like
Exactly right. They capture the most of the data. So think about when we were going back to our earlier example. This is important. We were going to have U1 and U2. That was like our basis, right? That's formally what it's called. We want to capture, so it turns out that the squares of alpha 1 and alpha 2 sum to the square of xi's components. Like their norms are the same, okay? That's just a mathematical fact because this is what a basis is. So the point is we want to capture of these two, we're going to throw away alpha 2 if we only are allowed to compute one component. So we want the U that we select to be the one that for most of the data captures some relevant information, right? Like if we found something like this direction is mostly orthogonal to where the line that the data lives on, so almost everybody's going to have like a projection that's really small. Like the data when I project onto the line is just going to be clustered really, really tightly together. Whereas if I project onto this line, it's still going to be nice and spread out. And this mathematically just says that it corresponds to either making sure that the alphas overall are very close to the x's, so they're larger on average, or that the amount that I lose, this is the residual, is the amount that I lose from the other directions is equivalently small. And for PCA and Euclidean space, this is the case. Not relevant for this class, but there are other kinds of geometries where that's not true. This happens to be true for Euclidean geometry. If you decide to take non-Euclidean geometry, it's a great course.
What is the superscript? Like,
This one. Oh, xi.
Oh.
Let me just write it again. Nice catch. Yeah, I's don't show up very well with this pen and my handwriting, which is criminal since we use them so frequently. Just assume it's an I. But that's all that goes on, right? So think about what this equation is saying, what this optimization is saying. It says pick over all the U's that are there. We're normalizing. We'll come back to why we normalize. It doesn't really matter too much. But what we want to do is explain as much of the data as we can. Okay? Awesome. So next time we will cover a little bit of eigenvalues and how we solve this. This is an eigenvalue problem. And we'll cover the cocktail problem as well. And you saw a little bit of PCA. Thanks so much for your time and attention. Talk soon.